Welcome to a lesson with Dr. Powell. Let's take a look at a special function which is defined in terms of another function, y is equal to sine x. So y equals sine x defines a curve. And in this function, a of x is given as the area between that curve and the x-axis up to a given x value. So from 0 up until an x value, you simply take the area to that point, and that's going to be the output of this function, which we'll call a of x. Now, what happens if this x value moves beyond this point where the curve is above the x-axis? Then we still take the area between the curve and the x-axis, but if we're on this side, we consider it as being a negative area. So we take a positive area up here and a negative area here, and we simply let a of x be the net area, meaning we add up all the positive areas and subtract the negative areas. So we have this nice area function that depends on the bound x as we go from 0 to x and find that net area. We're interested to know what the derivative of this area function is, and we're going to think about it intuitively and geometrically. So let's first of all think about how we would compute a derivative. A of x plus h minus a of x all over h, where h is like a change of x. It's like your run. And this up here is like how much the area is changed as your x value moves from x to x plus h. So that'd be like a change of area. So for instance, in a picture, this is the area at x, and this is the area at x plus h. And we're taking the difference between these two areas, and you end up getting a sliver of area right here. Now, this sliver of area is approximately equal to an area to a rectangle, where if you take the length of the rectangle, if you take, and you could even think of the rectangle as coming from with a height on the left side of x, and so maybe this rectangle should be drawn a little smaller to see that. Let's see, kind of thinking about this side right here. Okay, and so the height right here, right at the position x, this is x plus h. So right here at this point, this height is simply sine of x. So we can think that the change of area itself is approximately equal to sine x times change x right here. So change of area is approximately this. Now, if you're computing a derivative, we think about rise over run. So rise is change of area, and then the run is change of x. Notice what happens. A cancellation in this approximation, so we end up getting sine x. Indeed, the little sliver here, which actually is extra to this calculation, which is in addition to what we're actually getting for change of a, this piece itself in area divided by change of x actually goes to 0 in the limit of the limit computation for the derivative. So intuitively, we kind of see that as we move closer, this part really is almost nothing in comparison to this rectangle. So here we'll just kind of throw in an intuitive argument for that. But nonetheless, we can see that the derivative itself ends up being simply the height of the rectangle that we're working with as it moves to one point, and the width of the rectangle goes to 0. The height of the rectangle is nothing more than the y value of the function itself at the particular position x that represents the bound we're working with, that we're plugging in to the area function. So the derivative of a of x then with respect to x is simply the curve, the y value of the curve itself, sine x. Notice that this means that as the y value gets larger, the area is increasing faster. As the y value gets smaller, the area is increasing more slowly. When the y value is negative, that means the area is not increasing anymore. It's actually decreasing. Because we see actually the curve itself is the graph of the derivative of the function a of x. Thanks for watching.